Hey, here is again Pranav Sinha Chaudhary to start with the topic Hydrogenator Part 3. It's a continuation of Part 1 and Part 2. I have given the Part 1 and Part 2 link under the description box. Please refer it for your further assistance. Thank you for continuous support. Let's start with rotor surface heating. The generator rotor represents an excellent combination of electrical, mechanical, and manufacturing skills in which the field coils are well insulated, supported, and ventilated in a compound structure framework rotating at very high speed. Large hydrogenator rotor structure, that is salient pole, is relatively complicated, and the airflow process in the air gaps and between the rotating rotor magnetic poles with radiating fins is also very complicated. Furthermore, though the rotor always experiences great mechanical stress and high temperatures, in some cases up to 266 degree Fahrenheit to 311 degree Fahrenheit or 130 degrees centigrade to 155 degrees centigrade. While subjected to electrical voltage and current, it is expected to function for years together without failure. There are three design constraints that limit the size and life of the generator rotors. One, temperature, mechanical force, oblique stress, electrical insulation. The longer a generator is in service, the higher the probability that the soundness of the insulation of the rotor has been compromised by mechanical stress or heat-related factors. Any operating incident that induces heating can be detrimental to the insulation. Any abnormal operation includes motoring, a negative sequence event, closing generator breaker at standstill or turning gear or single phase operation, then flashing within the generator or an overspeed incident may have possibility to damage the insulation. The life expectancy of a generator rotor depends upon mode of operation, rotor design, and operating incidents. Generators that are operated as picking units with several start-stops and also with high var loads, high field currents rather, generally will have a lower life expectancy, much shorter than a base load unit with few start-stops and operating near unity power factor with lower field current. Picking units means hydrogenerators, and the base load unit is thermal units. Specific criteria for the change of rotor temperature. A, more frequent start-stops tend to induce more mechanical stress on the rotor insulation and will lead to more long-term deterioration and distortion of the copper conductors. B, operating incidents such as motoring or negative sequence operation can lead to rotor mass and retaining ring damage. C, incidence of high voltage spikes may cause insulation failures resulting of shorted turns and field grounds. Minimizing abnormal operational incident can prevent premature maintenance work. on a generator rotor and can prolong its useful life. Generator rotors that operate primarily at base load duty, that is for thermal generators, thermal units, and have minimal start stops can expect to have an average useful life of approximately 30 years. A unit operated in a frequent start stop mode can expect the insulation life of roughly 30% to 50% of that of a base load unit. Idle plants are generally operated as peaking units with several start stops. There are several heat sources in the large hydrogenerator rotor, mainly including copper losses of excitation windings and stray losses of damper windings. The phenomena of generator rotor thermal sensitivity may occur due to 1. An uneven temperature distribution circumferentially around the rotor, or number 2, by axial forces which are not distributed uniformly at the circumferential direction. Such occurrence is mainly caused by the large difference in coefficient of thermal expansion between the copper coils and the steel alloy materials used for rotor forging and retaining ring components. Whenever field current is applied and is made to increase, the copper tends to expand more than the steel forging. As the difference in expansion between the copper and the steel has become significant, then axial forces are generated. If these forces are not disturbed or distributed uniformly around the field circumferentially, they can cause generator rotor to bow. Basically, if the generator rotor winding is not electrically and mechanically balanced in the circumferential direction, then the rotor will be unevenly loaded, which can cause the rotor to bow, resulting the vibration to change with the variation of field current. Thermal deformation due to rotor winding interturn short circuit. In hydrogenerators, rotor winding interturn short circuit is a common fault. When there is breakdown in the insulation between turns that may cause certain numbers of shorted turns within the field winding, such fault would have to change the temperature characteristics of the field winding. Thermal stress distribution of magnetic poles in rotor winding and the generator has become unsafe to operate. However, generator operating problem is technically depending on the distribution and number of shorted turns of the field winding. Shorted turns in the field coils adjacent to the poles are most significant. The pole of the field with the higher number of shorted turns has a lower electrical resistance and as a result will be at a slightly lower temperature than the opposite pole. Therefore, the pole having higher temperature will elongate at the axial direction more than the other pole, and as a result, the field will bow in that direction. The amount of bowing will increase with the increase of field current, affecting the field vibration as well as rotor phase angle. So, shorted turns result in a reversible thermal sensitivity. Because of significant difference in thermal expansion coefficients between the rotor magnetic pole's core and the field winding, the thermal deformation would also be different with the change of the magnetic pole temperature field after the interturn short circuit, which would affect the rotor magnetic pole structure and the reliability of the generator. More the number of shorted turns, less will be the thermal deformations of the magnetic pole. But the case of non-uniformity of rotor winding deformation is aggravated. So, rotor field winding interturn short circuit will lead to have a thermodynamic change of rotor magnetic pole, and that will depend on the number and position of the shorted turns. It can be concluded that the interturn short circuit fault in the field winding would increase the imbalance of the thermal deformation of the field winding, decrease the thermal deformation of the magnetic pole, where to be turn shorted, and increase the thermal deformation of the magnetic pole carrying field winding further away from the shorted turn. One diagram for rotor field will blow in that direction. Interturn short in pole A, that is temperature induced in pole A, is rather greater than temperature induced in pole B. Generator configuration. In hydel system, for larger machines, the shaft orientation is usually vertical for stability and mechanical constructional point of view. Smaller units, even with fairly higher speeds, can be built with horizontal shaft. There are two types of vertical shaft generator categorized by bearing arrangement. One, umbrella type generators. These generators are equipped with bottom side thrust and guide bearings in combine and confined to low operating speed, that is up to 200 rpm, and at least expensive in and of least expensive in design. In semi-umbrella type generators, a top guide bearing is configured additionally. Umbrella or semi-umbrella design is being highly preferred as for low-speed vertical generator. Number two, conventional generators. The conventional design has comprised of top-mounted thrust and guide bearings supported on heavy brackets which are made the unit capable of supporting total weight of the generator. Thrust bearing supported bracket takes care the weight of generator rotating parts, turbine rotating parts, and axial component of water thrust acting on turbine runner. Guide bearing is provided to lock the rotation in the radial direction. A bottom guide bearing is usually provided in combination with turbine shaft. This conventional design is used for high speed up to 1000 rpm generators. Some medium size low flow turbine and tube turbine generators are of horizontal shaft. Direct driven bulb turbine generators are also horizontal shaft generators located in the bulb. Pelton type turbine coupled generators are mostly horizontal shaft. Hydropower generators are individually designed and built to fit a specific hydropower station depending on its location. Generator for the specific hydropower station is often assembled in the station site itself, where it is going to be installed because of the transportation limitations of a complete rotor and stator due to their massive size and weight. The assembly of generator at station site obviously needs high precision due to the design rigidity of tolerances required for the finished generator. Hydropower generators are driven by a turbine which is designed depending on the flow rate and head available, that is water head, at the site of the hydropower station. Points to be noted: hydro generators are of low speed machines and are constructed based on the mechanical consideration. Number two, for the given frequency, the low speed demands large number of poles and consequently large diameter. Number three, it is a normal practice to design the rotor to withstand the centrifugal force and stress produced at twice the normal operating speed. Types of bearing configuration. The position as well as combination of the bearings on the rotor shaft has a great influence on the construction of the generator rotor and the stator. There are 5 different combinations of bearing positions are usually configured as per shaft orientation. A. 2 guide bearings, one at top and one at the below of the rotor. One thrust bearing placed at the top of the rotor. Condition B. One guide bearing below the rotor. Combination of one thrust and one guide bearing placed at the top of the rotor. Number C, one guide bearing at the top of the rotor, combination of one thrust and one guide bearing below the rotor, and rest on the ground support. Number D, a combination of one thrust and one guide bearing placed at the below of the rotor, that is umbrella type. Number E, one thrust bearing is mounted on the turbine casing and one guide bearing is placed below the rotor. Now, bearing configuration of A and B, this configuration is applied for the generator of high speed and larger rotor length to diameter ratios. The stator frame has to rigidly constructed so as to be able to carry the rotor weight and the thrust load from the turbine. For configuration C, suitable for relatively large speed and rotor length to diameter ratios of 1/3. With the thrust bearing below the rotor and placed at the ground support takes care the weight of the generator rotating parts, turbine rotating parts, and axial component of the water thrust acting on turbine runner, and obviously relieves the stator frame from the load. This makes the construction of the stator frame less expensive. Configuration D and E. It is for slow rotating machines that do not have rotor length to diameter ratios that are larger than 1/4. Now, from the picture, you can easily understand what type of configurations, that is suspended type, semi-umbrella type, and umbrella type. Hydro generators are categorized by the position of guide bearing and thrust bearing. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments, feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you.